I think we are going to start here soon. I see John coming in here as well, so that's good. So this session is a little bit more of a deep dive. We have done 3 presentations on PlugFest results, which were, pretty technical also. But in this deep dive on AMI 2.0 applications, it will be more emphasis on the applications themselves. Like we're going to go through some of the applications and what they do and how they function more, and Carson's going to help me with that. And we also going to spend a little bit more on just not the communication networking needs, but also the compute architecture needs for AMI 2.0. So a little bit more on system architectures, and we will all, both Oleg, myself, and Carson, chip in on that. So it's just 3 main section here, and we still added in so that we're going to talk a little bit of experience from AMI 1.0, because it always helps to set the perspective as we go into AMI 2.0. And in AMI 2.0 section, then we'll spend quite a lot of time on the use cases, and then looking at the system architecture in general for AMI 2.0 and how to apply that on private LTE. So starting off with AMI 1.0, this one a slide we used for the PlugFest also, but just reiterate to get back into the groove here. So the use cases were pretty set for AMI 1.0 for quite a long time. So we had the meter data collection for meter to cache, change a little bit from daily to hourly, and now more towards the 15-minute read intervals. And that's sort of been the target now for the last few years. And then we have both individual reads and remote commands, like disconnect commands and so on, to take account also from smaller part of the population. And then we have the outage notifications, which need to be sent from all the meters that are impacted by a outage. And that can often, of course, be centered on the same sector or similar that you're actually getting your communication network from. So in that sense, it's very tight to succeed that on the life of the supercap, which is often just 60 seconds or even a little bit less sometimes on meters. And we have a firmware over there, which one we took just saying like on average maybe 1 megabytes for that. And when it happens on a certain month, then we always have tried to get to the whole fleet within 3 weeks. So that puts a little bit pressure on the downlink for that month when it's occurring. But this firmware OTA download could vary in size. So of course, in most cases, you try to do incremental downloads, but it could be bigger at certain cases, also need to be upgraded. So the next slide just shows these 2 architecture we had in AMI 1.0. Both have been deployed in scale. The one to the left is the larger mesh network with often a public LTE backhaul. So you would have cell sizes that are a few thousand meters often in the size, and you have often like multiple takeout points in form of access points, often on pole mounted. So you have the resilience in that way for the architecture. And then for the customers where we drove and deployed Direct Connect cellular, we often have used Cat M1 lately for that. And often it's been so far for AMI 1.0 on public cellular as well. And there, of course, we are mixed in with other traffic that could also be on the network for a public carrier. And what we experienced a little bit, like you only get allocated so much capacity also there. So we often had one Cat M1 channel to work on. And in certain sectors where we had a lot of devices, we actually had to work with our carrier to get additional channels in order to cope with the normal data collection requirements. And one of the big aspects there that we had maybe the biggest hurdles for us when it comes to outage management and so on was the number of connections that we could set up per second as we were trying to burst out a number of small messages. So eventually we had to tune sort of to 5-6 connection requests per second, and that's a little bit maybe conservative, but that was in order to not overload and congest and lose messages sent on the network. So if we looked at measurements of sort of the data collection portion in AMI 1.0, you see a graph here with a few different variants. So the RF LAN, which is the red portion there, and narrowband IoT, you can see how their graphs, when it comes to bigger sectors and sizes, so like in dense urban and so on, that actually it went up towards 1 hour to get all the meters read, which is of course not very good if you're trying to eventually have a 15-minute schedule. So the ones that succeeds best right now is the latest mesh, 802.15.4G Gen 5 mesh that we are utilizing, as well as Cat M1. So the Gen 5 is a little bit more efficient, as you can see, but also Cat M1 succeeds to get within the 15-minute interval if you do good pacing of all the meters. So to summarize for AMI 1.0, which has been going on for quite a while, what happened was like we got quite a lot of deployments of the 802.15.4G mesh network with public cellular backhaul, often in order to keep the lowest total cost of ownership. The cell sizes became fairly large because we were not pressured so much on latency in AMI 1.0. So we had often cell sizes of 1,000 or more meters per access point. There's a lot of, maybe not sort of thought about, but there's a lot of activities to optimize the usage of the network. So a lot of application pacing in order to spread the request on the network as much as possible. And it was quite hard to do a good outage notification service on the cellular Cat M1 and narrowband IoT because of the limitation on connection requests per second. So that's a little bit like where we were on AMI 1.0, and now we go to the AMI 2.0 side, and first I'm going to ask Carson here to take us through a little bit more in detail than we have done in previous presentations on the use cases.
Thank you, Jan. So kind of the core difference between AMI 1.0 and AMI 2.0 is if you look at this diagram, and it's quite simple from a picture perspective, but we're taking distribution level asset telemetry and pushing it down to the edge of the network, or to the consumers effectively. And when you think about reporting by exception and fine resolution data and in automation, this is kind of foundationally, it was in our power plants, it was in our transmission systems, substations, and distribution for decades at this point. But when you kind of move from a centralized generation model to a distributed generation model, the challenges with bidirectional load flow and kind of pairing the impact of large loads like EVs and managing your existing infrastructure challenge limitations really comes down to the low voltage network. And from a telemetry standpoint, the resolution of data that we had with AMI 1.0 was at best every 5 minutes. And so what we've done with the technology perspective is we improved the sensing capabilities of the meters. The technology in this space, there are ranges between 2, 4, and 32 kilohertz sampling, as well as reporting by exception and full capabilities of generating or applications that run on the meters. And what that allows us to do is extend visibility down to the edge of the network, so that we can understand not only what's happening from a power systems perspective, but also take control. And how you take control is in these metering platforms. It's not just 900 megahertz or cellular technology that extends comms back to the utility. There's an interaction layer from a communication standpoint using Wi-Fi to interact with assets in the home to gain access for control. And clearly, with the goals from our exercise here was to support kind of the interaction of responding to load and potentially taking action to protect transformers. And to accommodate that, there was 4 core use cases, and I'll go into them in more detail in the next three slides, and some of those folks who may have been in our earlier sessions probably seen this. But just to give you an idea, to enable these capabilities, we had to develop an application platform that allows us to modularly push applications to the meter that didn't impact the day-to-day functions. So when you get when you get a text message or you take a phone call on your smartphone device today, you're not worried that if you download the greatest version of Candy Crush that you're not going to be able to call your relative at the same time, because the core functions of making phone calls and sending text messages is separated from the various applications that run on the device. And so this concept is what we basically enabled on the next generation hardware, was a separated environment that allowed for modular applications to be deployed based on the utilities needs and core operations. So again, if there's interest in any of these applications in particular, beyond what I'm going to cover here today, please stop by. Happy to discuss in these full detail. But the core applications that we're going to talk in red relative to the study that we did are location awareness, which is effectively understanding the electrical connectivity of a meter, active transfer monitoring and voltage monitoring. Clearly, if we're going to take some type of action at the edge of the network to manage the grid, we have to kind of understand or have that real-time visibility of what's taking place there. And then certainly when you think about SCADA and AMS and control logic or control sequencing, we had to build an environment that allow us to layer different supervisory control rules on the platform itself to manage within various parameters to take action at the edge to meet both centralized goals and local goals based on system capacities. So when we think about location awareness and connectivity modeling, I used to work for Florida Power and Light as a power systems engineer, and we used to get quite frustrated when we get reports back and we expected a transformer to be overloaded, and it was supposed to be a 35 kVA transformer. We got out there and it was a 100 kVA transformer and was well within its capacity, or the vice versa. We were comfortable with the size of the transformer that was out there on the paper. We rolled out the truck because there was an outage and it was a 15 kVA, not a 75 kVA transformer. Or the mapping of the customers that are aggregated to the loading on that asset are incorrectly mapped, so our understanding of the active loading on that resource day after, because this was all consuming batch data, wasn't necessarily accurate. True story, it was Thanksgiving a couple years back, or many years back, I guess, and I was working the duty, and we had a power outage at one of the main areas of Miami Beach. And after I did the outage and I filed all the paperwork, got to work the next morning, and then one of my colleagues was like, he says, was it transport 123? And I said, yeah, it was transport 123. And we looked it up, and 3 times we'd been to the same location because the details about how the loads were associated to that transformer were all different within 3 years. And so what this does is allow you to dynamically know the electrical connectivity of any transformer in real time. So the meter itself, part of the capabilities, it has certainly has 900 megahertz, cellular options, PLC, and Wi-Fi. And we leverage the PLC very uniquely to establish a communication link between all the electric meters on that same secondary circuit. So we can reach out and literally measure and touch every device that's on the load side of that distribution transformer to give us confidence that we know that everybody's electrically connected to the same distribution transformer. And that, as I mentioned before, this new technology has the ability to sample sub-second. So again, 2, 4, and 32 kilohertz. So when we see the sine wave, we see zero crossing, we could take a snapshot of that time and understand relative to where our peers are electrically, to understand what my electrical contribution from a phase perspective is. So now I know how I am electrically connected to the transformer. I know what my phase contribution to the transformer is. And because I'm tracking each individual waveform anomaly over time, I can look at those signatures and distortions of the waveforms for voltage and current relative to each other. I could also assign who my asset from a substation, transformer, or feeder perspective is. So now when you think about it from the Holy Grail perspective of understanding the scale and scope of outages, ETRs, how my load is going to allocate to the various resources from a load distribution standpoint, this is a foundational app to accommodate that, and it's automated. To give you an example of the power that we did this, we were able to do, after the hurricanes this last season, able to identify all the meters that were impacted by outage and reconfiguration within 24 hours of the event of the storms that just hit Florida. So it's a quite powerful application. So now that you know how things are electrically connected, clearly when we start to think about the impact of various loads or new loads on the distribution assets, aggregating that loading to the core piece of distribution equipment that doesn't have visibility is foundationally the distribution transformer. So you have eyes on your reclosers, you have eyes on your cat banks, your feeder heads at the substation, but foundationally where the biggest change in load from a bidirectional load flow and impacts from an EV standpoint is effectively the distribution transformer. This is effectively ground zero when it comes to how we're managing the grid. And so because we can touch all those devices on that same transformer, we have the ability to aggregate the data amongst all those electrical peers in real time. And so because these devices have, they're communicating over PLC, they're sharing a bunch of different parameters, not just loading, active energy, reactive energy, demand, voltage, min-max, and average. You could push this data up to control systems in a one interval data in a consolidated packet from a single device, meaning that you're better leveraging your capacity of the network to provide even greater visibility than what you'd otherwise be using in traditional AMI 1.0. So this is literally SCADA level capabilities of visibility down to the distribution transformer. So once you have the monitoring capabilities down to the distribution asset level of the transformer, secondary bus, electrical connectivity, now you're looking at that hardware from a Wi-Fi standpoint. How can I reach in and touch and control that load to manage the limitations from a resource perspective? And so this EV SE management application allows us to leverage the Wi-Fi communication to be that transport layer into the home, into the smart devices that control the smart inverters or the EV charge controllers, leveraging standard-based communication protocols like OCPP, which is Open Charge Point Protocol, Modbus, Sunspec Modbus, or IEEE 23.5 to communicate to those devices. One, to get their specs and understand what they are that you're going to control, and then establish a monitoring session between that device and the loading on that premise, so you can manage the load on that premise within its panel schedule limits. You can manage the loading of the secondary bus limitations from an equivalent conductor capacity standpoint, and you can manage the limitations of the distribution transformer all in real time with 3 different control parameters, all from any of the meters acting as peers on that particular transformer. And so what this allows the utilities to do is not just defer investment upgrades, but by strategically managing these assets, you can prolong the life of these distribution assets relative to the new EV loads and also extend the resources for consumer. And earlier we had some benefit slides relative to this, but just to give you an idea, this is one of those win-win applications where not only does the utility benefit from a deferred cost perspective and operational maintenance standpoint, but even the consumers have a vested interest in allowing consumers to connect their resources because they could defer significant panel upgrades, which for some of our clients, averages about $1,500 to $2,500 per premise to upgrade their house for EV charge capabilities. So this is a win-win for both consumer and utility. And with that, I'll hand it back over to Jan. So if there's questions about this stuff, please stop by. Happy to talk about it.
Yeah, and we're going to hear from Carson again here in a few minutes on some of the compute architecture. So from what Carson talked about the applications, then we took those and looked at what do they mean in terms of network needs. And you almost heard it when he was describing how there was quite a few communications between meters and devices at the edge in order to handle transformer load correctly. And that's what we also see in the results here on the network needs. So you see a new type of communication that is meter to meter that occurs even for location awareness, but even more frequently for transformer load monitoring. You can see at it by default it's like a network, like a minute level communication that is needed, and that of course can be tuned a bit. I think Carson, there's some people may be running a little bit longer between the areas, but I also hear people maybe looking for even shorter time frame. And then transformer load management, that's where we actually come into the requirements more on strict latency, both for head and to meter, in order to act quickly and make any load shedding events. And then actually when you connect into EV chargers or inverters for performing those, it could be as the EVSE example, sub-second requirements on the latency just locally there behind the meter, and also reasonable, like 1-2 seconds for updating the head end and the user apps for changing shard rate. So that's a little bit what we see then new for AMI 2.0. And this one slide just shows it graphically, how we've been pretty steady on 0.5 to 1 megabytes per month for AMI 1.0, and as we started to add the transformer load monitoring, location awareness type of applications a few years back, actually starting, then we started first see a little bit of growth, both for the head-end traffic, but a new type of traffic that we call peer-to-peer. And as we go along and start now to see the control applications coming out here in the next few years, then those will actually put more and more emphasis on latency. And in order to wake you up and so on, we made the graph going just further higher. But as a reminder, like this is an application framework, so you can work both as utilities and partners and as Itron to come up with new use cases that can be solved with the meter. And one big area of that is the transactional energy market that could come in this period when these meters are out, and which will have a lot of more communication between neighbor prosumers that sell and buy electricity. So the network architectures one can think mainly about for AMI 2.0 is then either have sort of directly connected everything to the private LTE field area network, or as on the right side, having a smaller neighborhood area network that managing and taking the load of the local peer-to-peer traffic. And as we have seen it so far, it is very valuable to be able to offload that traffic, especially as we look at putting it on the FAN network on a private LTE. The side effect, which is a very important effect and benefit also with having a small neighborhood area network, is that we get a tool for coverage extensions to reach all the meters. So the summary for sort of AMI 2.0 before we go into architecture discussions is that we have this frequent peer-to-peer communication leading to that it's very valuable to have a neighborhood area network component in the architecture. We have increase in head-end to device-to-head-end traffic, maybe something around 10 times for the current set of application, and could increase. More importantly, also, we have predictable latency requirements, and that AMI 2.0 gets much closer now to DA type of SCADA applications, because you're actually working and trying to protect and manage the distribution grid elements. So from that perspective, having resiliency in terms of both private and public cellular fallback and so on, it becomes a very important portion here in AMI 2.0. And then we have the behind-the-meter comms to actually be quite low latency and should be reliable to the EV, solar inverters, storage inverters, and so on, where we're actually going to do the load shedding as needed. So we're going to go to the third section now, which is a little bit bigger, seeing on different portion of the system architecture. And Oleg will help us first to go through just the whole view of the connectivity architecture that is needed.
Thank you, Jan. Well, what a great show. So basically what we're learning here is that it's all about networking, and it makes me think that network is sort of I can call it the backbone of critical infrastructure, right? Because if there's no network, no connectivity, there will be no data. If there's no data, there's no decision, there's no outcome, there's no value. So networking seems to be sort of important for the future of energy delivery, of energy optimization. But the question arises, which network? And so this is a diagram, like a block diagram of our intelligent connectivity concept. So what you can see on this diagram looking from the like from the top to the bottom, or so it combines multiple networks. Then what we can see, there's maybe different geographical areas, maybe different technological requirements, maybe different commercial requirements. So there will be different networks that fit different needs, right? And then either we say this is public network, this is private network, or this is mesh network. All of these networks, they make sense in a certain areas, in a certain deployments. Now, of course, you can get like all these different networks, and from legacy point of view, we see that there's some utility deployments like with 5, 10, 15 different networks, and kind of it gets messy. But we will probably not get it all down to one single network. That's why we rather start working into optimizing the number of the networks. Let's take 3, and then however introduce the management tools that will help us to manage these networks more efficiently, and sort of like abstract the layer of the networks. So when you say this is a public network or private cellular network, well, technically it doesn't make any difference to the application, to you, because what you want to do, you need the data to be transported from the endpoint to the head end. Now, so managing and then augmenting this network with mesh, for instance. So as Jan was talking, there are some use cases where 95% of data stays behind the transformer within the mesh network. There's absolutely no commercial or technological point to send this data to the network. So it kind of makes sense to add this augmentation into the networking, and now introducing the management layer on top of these networks. And this management layer, what it needs to do essentially, it needs first thing to manage these networks efficiently, needs to like future proven, let's say, exchange this network. So when we're talking about cellular networks, then this is maybe you start deployment with public carriers, AT&T, Verizon, but then down the road you introduce your own private network. So this private network can be provisioned on the fly with these tools. Then there's a security layer on this network, so to make it robust and reliable. Then also like managing the outages of the network, managing the changes on the network over time. So all this is introduced through these tools. Now, let's say we can manage this network, we have all of this. Now we get the data to the IT OT center, right? So for IT, for managing this, so managing the data, managing the endpoints, and OT for managing the data and generate sort of a use case or value based on the use case on the application on this network. So this also needs, the connection also needs to be managed, because you have like multiple IPsec or VPN tunnels that will go into this IT OT. And then when you're working on multiple networks, each network is super independent, has its own core and has its own secure tunnel or multiple tunnels into the network. So you need to aggregate those and manage this also on the fly dynamically. And so all this is done through IT integration and then integration of this security. So now the interface between this network and the devices is typically the SIM card, right? So what you can see on the bottom there, and this is what I want to spend some words on the SIM card. So the traditional way, we will go to the carrier, get a SIM card, and we'll just plug the SIM card into a device. Now, when you have multiple networks, so as I said, multiple networks have their own cores, their own infrastructure. They also have their own authentication criteria. So basically what you need to consider is use this one SIM card to authentify, because most of the time, or oftentimes, especially on a lower data throughput devices, you have one SIM interface. So in this one SIM interface, if this is occupied with a SIM card with one carrier, with single SIM card carrier, then there's no way to do anything else. So now introducing the multi-network eSIM, where you can provision multiple networks and manage these networks on that particular SIM card, it just opens a variety of options how to connect and how to utilize the networks. And this is essentially what we do at Itron. We introduced this multi-carrier eSIM. This is fully GSMA standardized, and this eSIM can work in private networks, can work in public networks, AT&T, Verizon, FirstNet. So all of this can be put on one SIM card, and this SIM card can go into either meters or collectors, or any endpoints you can imagine on the network. So, and this is how we see the optimization of, or let's say abstraction of the network layer, and helping to consolidate this functionality and simplify, but also make it more reliable and robust. As I stated in the beginning, we consider network connectivity as the backbone of critical infrastructure. Thank you. Jan?
Thank you. All right. So I'm going to try and use the cursor on the computer. I promise I'm not going to go too into detail on how these processes work. This is just supposed to be kind of a simple data flow diagram of what's unique about the processes to enable edge compute. And so if we start from for the meter right here, hopefully you guys can see my cursor on the screen. Yeah, all right. The traditional, FAN or field area network, to backhaul to the head-end system, just the same as anything that we've done in AMI 1.0, and then that gets distributed to a message bus to any of the utilities operations, OMS, billing functions, etc. However, when we start to think about turning this into a extension of SCADA, we need to have a path to provide a streaming data set to control systems in isolation of the traditional data flow. And when you start to think about accommodating other third parties, we need to have a path to provide this data to enable those third party application providers an environment to consume this data and provide the outcomes or the data to drive the impact to whatever their use case is to the consumer. And certainly Itron, as we talked about, we have a number of applications, analytics that consume this data. So this is another box. It's a little bit new relative to AMI 1.0. And then this box here, the Itron Enterprise Application Center, you can kind of think of this as kind of like your Apple store, if you will. That's where when you want to modularly distribute a new application to a meter or a group of meters, support device management to manage those applications, that's kind of where all that action happens. And so, whatever application, whether it's third party or Itron, that's how you would manage what devices get which apps, within the system. And then when you start to think about having a mix of traditional AMI data, so 1, 5, 15, or hourly minute traditional AMI data, coupled with events and alarms that are tied to various applications, and then a combination of streaming data, 1 second or sub-second samples of 2, 4, and 32 kilohertz relative to waveform events or alarms. We had to have a path to provide this data for the utility to consume it and also those same third parties. And so we have this concept of Data Hub, which allows us to centralize those very different data sets and through APIs provide both Itron and other third parties and the utility themselves to subscribe to that data. Within that, third parties, you could also hit that to provide their access to, phone applications and things of that nature for, engaging the customers. And then, clearly, when you distribute the applications, on the platform, there's kind of three core components. There is certainly the metrology board like you would have in any meter that from AMI 1.0. There's the radio that you have to communicate on the network. But in addition to that, it's what we call a DI board, and foundationally, that's what allows us to run our edge components to support both the application management locally. So there's an operating system dedicated to run the containers that manage all the various applications on that hardware. And then what's a little bit unique in terms of our platform was, no one wants to talk about future-proof, right? Everyone gets scared about future-proof and commitments about, am I investing in the right technology when and where? And, you get into tech spec wars, right? But the concept of fog compute, or taking very complex problems and slicing them up into smaller components and distributing them to a bunch of different nodes or different computers on a common network that are networked, is not a new concept. However, what we've done with our application layer is, because we have peer-to-peer capabilities, the ability to distribute applications, solve those problems, and collectively, we actually, it's a force multiplier from a processing, a memory standpoint. So, we have the capabilities of leveraging meters that may or may not have a bunch of apps running on them, take advantage of that excess processing power to solve complex problems, and then send it to the peer that needs that data to make a decision. And it's a quite powerful concept, and we think that it's going to help us continue to provide an extensible platform for the future for edge compute with our customers. Clearly, some of the applications that we're doing with putting control logic into peers in the field is taking advantage of this today. All right.
Thank you, Carson. So those description here of the computing framework that Carson talked about, that has actually gone out in then smart meters like AMI2 ready smart meters probably for 5-6 years. And so as we looked at our latest data, it's probably like something like 11-12 million meters out there right now already with those capabilities, and about 9 million licensed apps that are gone out. And I think we have engagement with almost 11 utilities on this one. So we call it still early adopter scale, because it is a lot of learnings that always goes into this, but it is really moving forward pretty well. So to complement what Oleg was first describing of the overall intelligent connectivity framework, and then the distributed compute architecture that Carson talked, we'll just summarize back sort of more on the network again. So as we talked before, we felt and saw a sort of a good combination of having a field layer network largely based on cellular and fairly large in this case, and having fallback options and so on for resiliency, but complement that with a smaller neighborhood area network. So if we in AMI 1.0 had these two architectures that you see from the left and on the right on this picture, where we either had very big mesh cells or we had direct connect to the meters, sort of the sweet spots for going forward is going to be somewhere in the middle. We call it sort of a micro mesh architecture for the neighborhood area network, which is maybe 1 to 100 or similar like that when it comes to takeout points to and meters. And doing that, the architectural benefits we are seeking are to offload the peer-to-peer traffic from the field area network, so we can handle that just locally at the edge. Drive sort of predictable latency throughout the architecture from head end to meter. And we do that on two portions here, both that we have a flattened sort of micro mesh itself, which is only sort of normally will be 1 to 2 hops, but also that you can see we're more targeting a little bit bigger pipe on the field area network with LTE or 5G. We utilize the NAN network to handle any hard to connect meters so that we can get a reasonable investment for having 100% of assets covered. And we get this kind of two-tier, so we also can handle any longevity concerns when it comes to the public network fallbacks that are implemented in this architecture. and as such could consider that in a rate case one could have these takeout points replaced once, even if it's a 20-year rate case. And finally, going this architecture, it could gradually being flattened more and more as new applications come up. So it's sort of future-proofing for anything what's happened in the scale-up of new applications that we saw on the graph earlier on. And we added one slide just on sort of different neighborhood area network technology options that we are looking at for the future and so on, and what is available today. So a lot of the capabilities that we've seen and been used in the testing and other things for this Plugfest has been the Gen 5, which is an 802.15.4G type network complemented with power line carrier. And it has a lot of the tools that we need. We can create peer-to-peer in terms of actually direct communication between meters and actually broadcast over PLC as we need to all the meters under the same transformer. So very versatile in that way. What we are looking at just to see what all the alternatives and so on and where are we on that. So one view we had is like, what if we try to do everything on 3GPP cellular, so also the peer-to-peer. So then we started to be interested and started to talk with the ecosystem around something in peer-to-peer on cellular. And we've seen that a little bit in the automotive industry. They have something called SideLink. And in the push-to-talk industry, they have also something called proximity-based services. So those are not completely applicable right now to our use case, but we could evolve those probably in the 6G timeframe to be something that could be utilized for our industry with some effort. And the last, on the right side, your left side, you have also the an alternative to a sort of small style of RF mesh network, and that would be using Wi-Fi, and particularly something we think that has a little bit longer range, which calls Wi-Fi Halo. And the interesting of that one and why we're looking at it is that it's a little bit higher speed, so which we think we will need definitely over time. It's always good to have higher speeds. And also it has a lot of interworking with 3GPP cellular already in terms of authentication, frameworks and so on, as that combination has been used so much in the consumer industry. So these are three alternatives just to show that there is sort of more than one that one can go to. And we are looking at, over time, all the options that exist there. So that, I think, concludes our presentation. And thanking Carson and Oleg for being here and helping me, and also John Griebling here, who is our mentor for the whole team. And he's actually retiring here at the end of the year, and so I think you can give a big applause to John for all the things that we've done for UVB and Itron. You're welcome. Thanks so much. And if there are any questions to any one of us, we will stay around here. So.